Can you tell now at this point that things were rigged a little bit? So C and C, gone. What's the only thing left? Years. Is that a measure of time? Sure, I could change it to seconds, but years are a perfectly acceptable way of measuring time. So I check that to be sure my unit's right. And if I divide this in, 10 years, right? So we get 10 years to the nose. So that's how long the scientist on Earth thinks this trip takes. Okay. We good with that so far? When they arrive, have they aged 10 years by our reference frame? Doesn't this follow that thing I told you about the twin paradox? So by the time they get there, do they think 10 years have gone by? No, because basically I think their clocks are running slow, and because they actually accelerate and actually go there and whatever, then for them 10 years did not go by. They're not 10 years older by the time they get there. Okay? So now the next question is, according to a scientist on the spaceship, how long does this trip take? What information do I need? Okay, to get time, I need the distance and the speed. So if I'm on the spaceship, first off, do I think I'm moving?
No.
What do I think is happening? We have a wild star, and the star is charging us at a rate of 0.9 c. But how far does that star need to travel? Just to be where you are, or something, however that song goes. Say what? All right, so exactly what happens is that we have a length contraction taking place, right? Because I'm moving through, or the star is moving through that distance that I'm trying to go. So basically what we're saying is in that reference frame, we've got to contract the length by a factor of gamma. And tell me, without actually putting numbers in right away, what is gamma in this case? Let me just set it up. It's 1 over the square root of 1 minus
d squared over c.
Okay, d squared over c squared, and d squared is 0.9, so I have 0.81, right? 0.9 squared is 0.81.
Yeah,
If I say so, I could be wrong.
you're right.
With Sam saying I'm right, I'm not going to argue with him all day. All right, so what do you get for gamma when you plug in numbers? Say what? First question, does that pass the believability test? The thing I'm saying, I don't know if it's the right number, but what's something that it must be? Greater than 1, and it is. So at least that seems like a reasonable number. If I got 0.29, I'd have realized I made a mistake. But the fact that it's bigger than 1 gives me at least a little bit of hope that I'm in the right direction, or at least I haven't made as many possible mistakes as I could have. All right, so we've got gamma is equal to this. Now, length contraction. This is the proper length. We already figured that out. That's 9 light years. All right, and gamma is 2.29. All right, and where do I go from there? Pretty easy. I don't have to worry about light years are already the right units, so I simply divide by that and tell me what number you get with your calculators. 3.9. 3.83. Is that what you said?
3.9.
3 point.
All right, I'll stay with 3.9. All right, so 3.9 light years. Okay, so I've got that distance. That's looking good. But I'm on the thing, and I want to find out how long do I think that's going to take. So if this is the distance I travel, how fast do I think the star is moving? I think I'm sitting still, but the star's got this much distance to travel, and it's moving at 0.9 c. So the time that I expect is 3.9 year times c and a speed of 0.9 c. Again, the c's cancel, and we should get 4 point something. 4 point what? 4.4? All right. So 4.4 years. Big difference, right? Big difference. So just think of all that youthful time you've had where you could have been 10 years older, but you're only 4.4 years older. What did you do with those other 5.6 years? I'm not even kidding. What did you do with those other 5.6 years? That the people on Earth thought it took you, but it only took you 4.4. Did you enjoy 5.6 years at the same age? No, they never happened. And that's what's weird. They never happened. You didn't feel like you stayed young longer. Never happened. Time just went by. The same as it always does. For you, it's just 4.4. That's literally so that if you come back, everybody else is going to be old. But it's not like you spent a lot of time being youthful. To you, that time never happened. And that's what's weird about relativity. Okay, so we got the time being 4.4 years. Now, according to the scientists on the spaceship, what is the distance traveled during the trip? Oh, well, you know what they did was, that's fine. They used gamma instead of what we did, but that's all cool. All right, so they just asked questions that we've already answered. So the thing is then, guys, I guess what we come back to is this. When you're doing questions in relativity, the biggest important thing is first think of reference frames. Draw pictures. You've seen my artwork. I know it'll be hard to match the elegance of my pictures, but try. No, the thing is, choose your S frame, choose your S prime frame, understand your Lorentz equations. Now, where the Lorentz equations come in, why didn't I need the Lorentz equations for this problem? And what physical situation makes us need Lorentz equations? When you have some other object inside a frame with motion. In other words, what we've got is an S frame and an S prime frame, and there's one v, a speed at which they separate. But if a u, another velocity within one of those frames takes place, we need the Lorentz to figure out how fast that looks in the other frame. So if I know a u in the S frame, I need these equations to find u prime, how fast it looks from the other frame, or vice versa. So you just need to know when to pick these. This is how fast it's measured in the S prime frame. This is how fast it's measured in the S frame. V is the only thing we need if all we've got is separating frames. And with a rocket leaving Earth, that's all we have. If the rocket had velocity, if the rocket decided, oh, let's fire a search satellite to go there ahead of us to make sure it's safe to land there, so they shoot it off even faster than they're traveling, so it gets there first. What would happen then is, we'd need to use Lorentz transformations to find out how fast that's moving in, say, the Earth's frame as compared to their frame. Okay, so I have the following situation. In my reference frame on Earth, how quickly are these rockets approaching each other? And you shouldn't need to do a single pencil to paper calculation. Even though the answer will make you wiggle a little bit because you don't want to believe it. 1.6 c. But I thought nothing could go faster than light. Nothing is. Right? What it is, it's the relative approach. From my point of view, if there was one light between them, they would cover it twice as fast because each of them is coming at their own velocity. So their rate of approach is literally just the sum of their velocities. But if I now ask, how fast does this rocket think this rocket is going? That's a different question. And now do it. How fast does the guy in the left rocket think the guy in the right rocket is going? What's going to make this tricky, guys, is choosing your S frame and your S prime frame. That's what makes it a little tricky, so be careful about that. And I will give you a hint by saying the guy on the Earth is absolutely essential to solving this problem, because he's the only one who knows the velocities. All right? So the guy on the Earth is absolutely essential. Oh, and by the way, yeah, don't hesitate. If you want to talk to each other, that works too. But just don't tell lies to each other. Or tell lies and make sure you're the only one in the room who gets it right because you've misled everyone else. That works too, I guess. That's not seeing anything that I'm doing, is it?
It is.
Is it actually a video?
Oh yeah.
It makes me nervous. I don't like cameras pointed at me.
Me neither. But I'm
You're
on.
not, I was gonna, you're not sitting here where it matters.
Exactly.
If I were where you were, I'd be happy.
I'm going this way if it makes you feel any good.
Has anybody actually finished calculating the number? If I doctored one of those numbers, would it be okay? Because I realize the symmetry of this is going to make it crazy. So I'm going to actually change this. If this doesn't mess, well, even if it does mess you up, so what? All right, I'm going to change it because otherwise you're going to get lost as to which one is which. Does everybody recognize that there are at least two very good ways to solve this problem? Okay. Do I need to nudge us all a little? If I tell you that I think this is the S frame, does that work for you? All right, I chose the guy on Earth as the S frame. Guess which frame I chose as the S prime? It would literally just be a guess. There's no way to know because either of the other frames is just fine, except that what I did ask is how fast does this guy think this guy is going? That means this is the most logical choice because that way I know how fast this guy's going in my frame. I want to know how fast he's going in your frame. So what do I name this velocity in my reference frame? U. Because velocities measured in my reference frame are given U. What velocity do I want for this frame? U prime. Velocities measured in this frame. So this is what I don't know, it's what I want. Now, do you understand what we just did to solve the problem? From here it's just plug chug. So, although that's the part that you sort of, whatever, and you blow past it, that's the solution. Everything after this is algebra. So let's go through that again. I'm the one who knows the answers. I'm seeing the velocities of both. I choose me to be the S frame. I know how fast this is going, I know how fast that's going, and I want to know how fast does he think it's going, so it's easiest for me to make him the S prime frame. I could make this guy the S prime frame and then say, whatever answer he gets for this, because their motion is relative, the other one is just the same answer but the opposite sign. But we don't need to go there. This is the easiest way to choose it. So, what I want is U prime, and from the equations we have over there, I see that U prime is equal to U, I'm on the first one over there, minus V over 1 minus U V over C squared. Let's plug numbers in. What is U in my frame? Be really careful.
Negative 0.6.
Negative 0.6 C. Right? It's a velocity. So we indicate direction by the sign. Negative 0.6 C minus V. And what's V? What is V? It's a logical thing. It's the reference frame velocity, right? It's the velocity of S prime in the S frame. In my frame, how fast is S prime going? It's the 0.8 C, right? That's how fast this reference frame, the rocket ship itself is going. So, and I minus it from this, so I get 0.8 C. It's not because this is a negative 0.8 C. It's because the equation has me put a minus sign. All right. Then, in the bottom, I have 1 minus, and it's the same things again. U is minus 0.6 C, and then it's times 8, not negative this time, 0.8 C all over C squared. So the C squareds cancel. and I have negative 0.6 times 0.8 is 0.48, but I have another negative, so I get 1.48 on the bottom. On the top, I have negative 0.6 and negative 0.8 for a negative 1.4 on the top, which equals negative 0.95C, more or less. So the question then comes, does that answer make sense? I mean, at this point, I can't say definitely that's right, but what are some of the emergency flags that should go off if I get a wrong answer there? Number one, does it have to be negative?
Yeah.
Yes, because if I've got the guy in that 0.8C rocket ship going this way, there's no way he's not going to see the other rocket ship coming towards him, right? So that does have a negative sign. Could it ever be greater than C at the end? No, and it's not. So at those two levels I'm comfortable. It may be numerically wrong, but my method is right. Is everybody seeing that okay? Do your brains hurt yet? Just a tiny bit? I haven't done anywhere near my job then. So guys, what I want to do here is just take about a 5-10 minute, get some oxygen back in your brain, come back and I'm going to tie a few things up and then I'm going to let you go. All right, just take a little break so that you're not just listening to